In this example, we are looking at the college enrollment in private colleges within the United States. We are told to use X for the years since 2004 and Y for the enrollment in millions. So looking at my data, based on what it told me, when we have 2004, that is actually an X value of 0. 2005 would be 1, 2006 would be 2, 2007 would be 3, and 2008 would be 4. So we look at what we're supposed to do with this data, and it asks us first to complete the table of differences and then discuss observations. So down here at the bottom of our screen, we have the table of differences, and we see that the X is from 0 to 1, and we already labeled our data, so we know that's this first year. So we want to know what is the change here in the Y value. So I would have to take 4.47, which is my Y2, and subtract 4.29, which is my Y1. I'm actually doing this block right here, and doing that math gives me a value of 0.18. So the change between these two, the enrollment has increased by 0.18 million. So now I do my next pair, and again subtracting Y2, so 4.58 minus 4.47, and do that math on my calculator, and I get 0.11. So this is an increase of 0.11 million. I do the next pair, so same idea, 4.76 minus 4.58. Do that math on my calculator, and this time I get 0.18 again. And I do the last pair, and so I have 5.13 minus 4.76, and that is a change of 0.37. So when I have done this, I am to look at this and I see that they are not constant. But rather they are random. So it is based on this observation that they are not constant but random that I'm going to make decisions moving forward of how to model this data with what type of equation. We know that constant change is linear. And we have observed that things like increasing, which would be going up in value, which this data definitely is, from 4.29 to 5.13, so it's increasing at an increasing rate, or at a decreasing rate. Either one, different, but either one would result in a distinct curve. And curves tend to have equations as well. But when I look at the amounts of change, we have 0.18, 0.11, 0.18, 0.37. They are not exhibiting a pattern. So they do not get bigger as I go through them, or they do not get smaller as I go through them. If this first number was smaller than 0.11, so like 0.04, then I could say that it would be increasing at an increasing rate, because my numbers here, if I had a 0.04, would be getting bigger each time. But I don't have a 0.04. I have 0.18. And so I see that the increase is different between these two and these two and these two, and so it is truly random. So when we have this randomness, this is almost linear. And most of the time, not always, but most of the time, that randomness will be best approximated by a line. It will not be perfectly approximated, it won't perfectly match the line, but it would be close. It would be scattered around a line. Now we're going to do a lot of calculator work in this problem. So it asks us next to plot the data points. And so I'm going to go to my graphing calculator. And before I go there, I want to show you all kinds of steps. So here I have all kinds of steps to use the TI 83 or 84 calculator. And so we are going to go and actually do the work on the calculator, but if you need to write some steps down or you have to go back and look at them, you can come back to this slide and pause the video. So anything that's in this little box like this is a button push. So we're actually going to push the stat button, push enter, and that's going to allow us to edit. Again, here we're going to push the stat button, push enter, and then down here we would push the clear, push enter. So those things that are bracketed off are actual button pushes. So here I am in my graphing calculator, and I want to put the data in to plot the points. So I hit my stat button and I hit enter to edit it. Now I see that I have data in here from a previous problem, so in order to clear it, I arrow up until the list name is highlighted and hit clear and hit enter. And then I can go over here, list 1, arrow up, hit clear, and hit enter. So list 1 is my first list, or my X values, and we had said that they were 0, 1, 2, 3, and 4. Then I can go over using my arrow to my list 2, which are the Y values, so 4.29. And you'll notice I'm pushing enter between each and every one of these. 4.47, 4.58, 4.76, and finally 5.13. Now, I would like to see these points, so I'm going to set up my window so that I would see them. So in my window, my X values were from 0 to 4, and my Y values ranged from 4.29, so I'll start a little below that at 4, up to 5.13, so I'll go a little bit above 5.5. And so now I have a window where these that would totally cover the data that we have. But I do not have an equation, so the next thing I have to do is go to my stat plot and turn that on so that I can plot the data itself. So I'll use second and my Y equals. And you can see that all of my plots are off here. I'm going to click enter for plot 1. And I want to hit enter to turn it on. I want the first type of graph, which is just plotting of the points based on list 1 and list 2. And I'm going to have this little square show up wherever a point is. And this is the color edition, so those are going to show up in blue. So all of that looks all set, and I hit graph. And here are my points. So again, in your video, you can pause on this screen if you would like to go through those directions. It explains exactly what we did. Back to our problem. It says, is it reasonable to approximate the data with a straight line? The answer is yes. When we looked at the data, they weren't far from a line, and we explained up here because the change was random, it was almost linear. The next thing we're asked is to find a regression equation for the data. Because the slope varies throughout the data, our calculator will use a least squares regression, which is a calculus idea, and it will find a best fit line. So we're going to go to our calculator and find the equation using our calculator. So in my calculator, this is a statistics feature, so I'll start with hitting the stat button. And this time, instead of editing the data, I want to calculate, so I'll move over using my arrow key. And I would like to find a line, so you see option number 4 here is a linear regression, and they use ax plus b instead of mx plus b, but you can see that that matches up, so I hit enter. It's asking me here, do I want to use the x as list 1? Do I want to use the y as list 2? The frequency would only be if each data point was more than once, so I'll let that unchanged. I could store my regression equation. I'm not going to worry about that at the moment. And then I get to calculate, which is where I hit enter. So my calculator has done all the work of approximating or averaging out the slope of a line to fit this data. So our slope is 0.197 and our y-intercept, our b value, is 4.252. So in here, find the regression equation. We did that and we got y equals 0.197 x plus 4.252. It then asks us to graph this on the same window. So we'll go back to our calculator. I'll go to my y equals. I'll type in this equation that we found. And we are ready to set up our window so we can graph, and we see that picture where the line is a great approximation to these actual values. Looking at this, it says explain the meaning of slope. So right here, the slope of 0.197 would mean that enrollment increases on average by 0.197 million per year. It says express using function notation the enrollment in 2003. So using our function notation, this would be y. 2003 is a year before 0, so at -1, and we'll find the answer. And then it asks us also for 2014, so that would be y, and that would be 10 years after 2004, so of 10. So we'll look and find both of those answers with our calculator. The easiest place to find these answers is in our table, so I'll set up my table. I'll start it at -1 because that's the first value that I want, and I'll have it go up by 1s. So then if I take a look at my table, it predicts that the enrollment in 2003 would have been 4.055, and scrolling down a bit, in 2014, 6.222. So this first one is 4.055, which is very, very close to the 4.05 that was actual. This last one we found 6.222, which is not close to the actual. And that's because we would expect that in 10 years' time, the trend would change. So throughout this video, one of the things that we wanted to see is that if the change is random, then we can approximate the data with a line. We also wanted to see how to use our graphing calculator in order to put the data in and find a regression equation. And if you back up in the video, you can pause it on the slide that has the keystrokes, and I showed you that on the calculator itself.